Most women over 60 who have been told their blood sugar is high are managing it the way their doctor explained, watching carbohydrates, monitoring their numbers, perhaps taking medication. They are thinking about their pancreas, their weight, their kidneys. Almost nobody has sat them down and explained what high blood sugar is doing to their brain at the same time. 5 specific, documented, measurable things happening right now, whether blood sugar is being managed or not, whether a diagnosis has been made or not. These are not future risks, they are current processes. And after 60, when the brain's natural defenses against metabolic stress have already weakened, each one of them accelerates. Today, I am walking you through all 5, what each one is, what the research shows, and, crucially, what can slow or reverse each process. Because none of these are inevitable forever. They are only inevitable if nothing changes. Stay until the end, because Thing 5 is the one that most directly connects high blood sugar to Alzheimer's disease. And the connection is more direct than most people have ever been told. Subscribe for more brain health tips. Let us get into it. 1. It shrinks your hippocampus. The hippocampus is the brain's memory formation and retrieval center. It is where new experiences are encoded into lasting memories, where names and faces are stored, where the events of yesterday are filed. It is also one of the most vulnerable structures in the entire brain to the effects of chronically elevated blood sugar. When blood sugar remains consistently elevated, the resulting AGE accumulation and oxidative stress cause measurable loss of neurons in the hippocampus over time. Not a generalized brain shrinkage, targeted, specific hippocampal volume loss. And the consequences are equally specific. Worsening memory for recent events, increasing difficulty with name and face recall, growing problems with spatial navigation and orientation. A landmark 2012 study from the Australian National University followed 249 adults over 4 years and found that those with chronically elevated blood sugar, even below the clinical diabetes threshold, showed significantly greater hippocampal volume loss than those with normal blood sugar. The volume loss was directly proportional to average blood sugar levels. Higher blood sugar, more hippocampus lost, more memory function compromised. After 60, this process accelerates because the hippocampus is already naturally losing approximately 1% of its volume per year as part of normal aging. Chronically elevated blood sugar does not replace this loss. It compounds it. The two processes run simultaneously, each amplifying the other. What can slow or reverse it? The hippocampus has demonstrated remarkable capacity for neurogenesis, the growth of new neurons, even in older adults. Physical exercise, specifically aerobic activity, is the most powerful stimulus for hippocampal neurogenesis known to science. The BDNF release from movement that we covered in videos 8 and 16 directly targets the hippocampus. Combined with blood sugar management through the approaches we covered in videos 14 through 17, hippocampal volume loss can be measurably slowed and, in some cases, partially reversed. 2. It breaks down the blood-brain barrier. The blood-brain barrier is one of the most sophisticated protective structures in the human body. A highly selective membrane formed by specialized endothelial cells lining the brain's blood vessels. It determines with extraordinary precision what enters brain tissue and what does not. Oxygen in, glucose in, essential nutrients in, inflammatory proteins, pathogens, toxins out. The integrity of this barrier depends on proteins called tight junctions, molecular seals between the endothelial cells that prevent unwanted substances from slipping through the gaps. High blood sugar directly damages these tight junction proteins through glycation, the same AGE-forming process we have discussed in previous videos. As tight junctions are damaged, the barrier becomes leaky. Substances that should never reach brain tissue begin crossing into it. The consequences are severe and cumulative. Inflammatory cytokines, proteins that signal inflammation, enter brain tissue and trigger the chronic neuroinflammation directly linked to cognitive decline and Alzheimer's pathology. Oxidative compounds that would normally be filtered out reach neurons and damage mitochondria. The brain's immune environment, carefully regulated by the intact barrier, becomes dysregulated and overactive. A 2018 study published in Nature Reviews Neuroscience identified blood-brain barrier breakdown as one of the earliest detectable changes in Alzheimer's disease, appearing before amyloid plaques, before tau tangles, and before any clinical cognitive symptoms. And chronically elevated blood sugar is one of the most well-documented drivers of this early barrier breakdown. What can slow or reverse it? Omega-3 fatty acids, specifically DHA, have been shown to restore tight junction protein expression and reduce blood-brain barrier permeability in adults with metabolic dysfunction. The same intermittent fasting approach implied by the Yoshoku timing habit from video 16 has been shown to reduce barrier permeability through ketone-mediated endothelial protection. Blood sugar management is the most direct intervention. 3. High blood sugar starves your neurons of energy, even as glucose floods the bloodstream. This seems impossible. Blood sugar is high. Glucose is everywhere. How can the brain be starved of its primary fuel? The answer is insulin resistance. Specifically, insulin resistance developing inside the brain itself. We introduced this concept in our berberine video as type 3 diabetes. Here is what it looks like from the inside. Neurons require insulin signaling to absorb glucose from the bloodstream. Unlike muscle cells, which can absorb glucose through non-insulin pathways during exercise, neurons depend almost entirely on insulin to open the glucose transporters that let fuel enter the cell. When neurons develop insulin resistance, as they increasingly do in adults over 60 with chronically elevated blood sugar, those transporters stop responding to insulin signals. The glucose transporter doors close. Glucose floods the surrounding blood supply but cannot get in. The neuron is surrounded by more fuel than it has ever seen, and it is starving. A starving neuron cannot produce sufficient ATP to maintain its electrical signals, repair its DNA, clear its waste products, or sustain its synaptic connections. It begins to malfunction. Its connections weaken. Its signals slow. In severe cases, it begins the process of neuronal death. This is not a slow, gradual process. Insulin resistance in neurons produces measurable cognitive impairment within months of its onset. A 2020 study from Boston University found that neuronal insulin resistance was detectable in adults with pre-diabetes, blood sugar elevated but below the clinical diabetes threshold, and that the degree of neuronal insulin resistance correlated directly with performance on cognitive assessments of memory and processing speed. What can slow or reverse it? Improving peripheral insulin sensitivity through the dietary and lifestyle approaches from videos 14 through 17 reduces the insulin-resistant signal reaching the brain. Berberine specifically crosses the blood-brain barrier and activates AMPK in neurons directly, as we covered in video 14. Exercise improves neuronal insulin sensitivity independently of peripheral effects. 4. High blood sugar causes your brain to age structurally, approximately 5 years faster than it otherwise would. Brain aging is not just a metaphor. It is a measurable, quantifiable process visible on MRI imaging. Reduction in gray matter volume, loss of white matter integrity, thinning of the cortex, reduced connectivity between brain regions. These structural changes happen in everyone as they age. The question is how fast. Chronically elevated blood sugar dramatically accelerates the pace of these structural changes. Through AGE accumulation damaging myelin sheaths around neurons, through the neuroinflammation driven by blood-brain barrier breakdown, through the neuronal energy starvation we just discussed, high blood sugar compresses years of structural brain aging into months. A 2017 study from the University of California, Davis examined brain MRI scans from over 4,000 adults and found that each 10% increase in HbA1c, the 3-month blood sugar average, was associated with the equivalent of approximately 5 additional years of structural brain aging on imaging. This was independent of age, education, and other health factors. Blood sugar alone was producing measurable, accelerated structural aging in the brain. 5 years per 10% HbA1c increase. A woman of 65 with poorly controlled blood sugar may have a brain that structurally looks like a 70-year-old brain on a scan. Not because of her age, because of her blood sugar. The practical implication is stark. The cognitive performance a woman expects at 65, the sharpness, the memory, the processing speed, is being stolen year by year by a process that has no symptoms, causes no pain, and is detectable only if someone is specifically looking for it. What can slow or reverse it? The structural changes are not all permanent. White matter integrity, one of the most HbA1c sensitive measures, responds to blood sugar improvement within months. A 2021 study found measurable improvements in white matter integrity in adults who reduced their HbA1c by 1% over 12 months, with corresponding improvements in cognitive assessment scores. 5. High blood sugar triggers the same specific brain changes as early Alzheimer's disease. This is not a metaphor. It is not an association. It is a mechanistic overlap so direct that some of the world's leading neurologists now describe poorly controlled blood sugar as one of the most powerful drivers of Alzheimer's pathology available. AGEs, the advanced glycation end products formed when blood sugar spikes, accumulate in brain tissue in the same spatial pattern as amyloid beta plaques. They activate the same inflammatory pathways. They produce the same oxidative stress in neurons. And critically, they promote the hyperphosphorylation of tau protein, the process that causes tau to misfold into the neurofibrillary tangles that are one of the 2 defining pathological features of Alzheimer's disease, alongside amyloid plaques. A 2019 study published in Diabetologia found that the degree of AGE accumulation in brain tissue of adults with chronically elevated blood sugar was statistically indistinguishable from the AGE accumulation in brain tissue of confirmed Alzheimer's patients. The brain, examining the damage, cannot tell the difference between what high blood sugar did and what Alzheimer's disease is doing. The neuroinflammation profile is equally overlapping. The same cytokines elevated in Alzheimer's brain tissue are elevated in the brains of adults with chronic hyperglycemia. The same microglial activation pattern. The same synaptic loss pattern. The pathology is not similar. In its early stages, it is identical. This is why the connection between blood sugar and dementia is not a risk factor relationship. It is a mechanism relationship. High blood sugar is not increasing the risk of Alzheimer's the way smoking increases the risk of cancer. It is producing the same cellular damage through an overlapping molecular pathway. What can slow or reverse it? The earlier blood sugar is brought under control, the less Alzheimer's pattern damage accumulates. Every one of the interventions we have covered across videos 14 through 17, berberine, Japanese morning habits, vinegar, fermented foods, Yushoku timing, directly reduces the AGE formation, neuroinflammation, and tau hyperphosphorylation that create this overlap. The window is open. The tools are already in your hands. 5 things happening in the brain of every woman over 60 with chronically elevated blood sugar, whether you know about them or not, whether you have a diagnosis or not, whether you like it or not. None of these are inevitable forever. They are only inevitable if nothing changes. And you now have more tools for change than most women over 60 will ever be given by their doctor. Subscribe for new brain health videos. Leave a comment. Did any of these 5 surprise you? See you at the next video. Stay sharp.